Problem number 11. We are told that we have an imaginary zero at 2i, and we want to find all the zeros of the polynomial. Well, remember that complex solutions always occur in conjugate pairs. So if I have a solution at x equals 2i, I have another solution at x equals negative 2i. That is the complex conjugates theorem. Is that a thing? Yeah, I think that's what it's called. Okay, so that's complex conjugates root theorem, tells us that. But we also know that the linear factorization theorem says if we have a complex solution, then we have a complex factor at x minus the solution. So I know I have a factor at x minus 2i and another one at x plus 2i. Cool, so what? How does that help me? Well, FOIL it. What do we get? We get x times x is x squared. We get x times 2i is 2xi. But then we get negative 2i times x is negative 2xi. So those cancel. And then finally we get negative 2i times positive 2i is negative 4i squared. So what does this become? This becomes x squared plus 4. Because I squared is negative 1. Negative 4 times negative 1 is positive 4. Or you could remember that when you multiply complex conjugates together, you're going to get a squared plus b squared. So that's cool, I guess. Well, what now? Well, x squared plus 4 has to be a factor of this polynomial. So let's divide it. We want to divide x to the fourth plus 7x cubed plus 10x squared plus 28x plus 24 gross by x squared plus 4. So how do we do that? Well, we ask ourselves a question. X squared times what is x to the fourth? Well, x squared times x squared is x to the fourth. So x squared times x squared is x to the fourth. And x squared times 4 is 4x squared. Notice where I wrote that. That 7x cubed does not have a pair. That's going to be dropped down when we do our subtraction. Some people put a 0x cubed there. Totally fine if that makes you feel more comfortable. I don't feel the need, so I'm not going to do it. But x to the fourth minus x to the fourth is 0. Happy. 7x cubed minus, if we have a 0x cubed in there, doesn't do anything. So we get 7x cubed. And then 10x squared minus 4x squared is a 6x squared. And let's drop this 28x down. And let's play the game again. We say x squared times what is 7x cubed? Well, it's got to be 7x. 7x times x squared is 7x cubed. 7x times 4 is a positive 28x. And again, we have that awkward gap, and that 6x is just going to drop down because it's like we have a 0x squared in there secretly. And we're subtracting this whole thing, and we get 7x cubed minus 7x cubed is happy face 0. And we get 6x squared minus 0x squared is just 6x squared. But look, we get 28x minus 28x is 0x, which is kind of sweet. And we drop our 24 down now. And we play the game one last time. We say x squared times what is 6x squared? Well, x squared times 6 is 6x squared. And 6 times 4 is 24. So look, we have a 0x term, and we're actually happy about that because we're subtracting this whole thing, and we get no remainder, which means that weird complex stuff actually worked out. And so what is our quotient? Our quotient is x squared plus 7x plus 6. So I know stuff. What stuff do I know? Well, x squared plus 7x plus 6 can be factored as x blah times x blah. What's the blah? Plus 6 and plus 1. So if I write this completely factored, I have x plus 6 times x plus 1 times x minus 2i times x plus 2i, which is gnarly. But that's what I started with. That is my y equation completely factored under the complex number system. And I haven't answered the question because it says find all the zeros of the polynomials. So my zeros are x equals -6, -1, 2i, and -2i. Don't forget the imaginary ones because they're real. Ha 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 ha. Math language joke.